Welcome back, my name is Jesse, I am a tutor in Melbourne and I'm also making GAMSAT videos as well. What I'm trying to do is I'm trying to basically just create a whole lot more free resources for people to help increase kind of the questions available, higher quality resources to help people prepare for the GAMSAT, whether you're sitting in March or September. The March sitting for 2022 is coming up pretty soon, and I know people are really looking for extra material beyond the official ACE material. If you've already exhausted all of that and you're looking for more practice for section 3, then these questions, I try to write them up. I put them up on my resources page, which I link below as well. And this will kind of act as a bit of a walkthrough video so that it's a worked solution. So if you want to kind of go through the questions first and then watch this to kind of check the reasoning, but you can also watch it as well. A lot of people find it helpful to see how I would actually tackle a question as well and how I might work through it. All right, so what we'll do, we'll go through a new one here. This is now, I think this is set number 10 we're on now actually, and this should be on the resources page in the table kind of further down the bottom underneath the essays for section 2. Yeah, you can open up there, you can access the questions there and have those open while you work through it. So we've got two stems that I've put together. We're going to look through some organic chemistry, and again, it's not really based on the theory all that much. There's a little bit of theory. I try to, in my videos as much as possible, show why you don't need to know a huge amount of theory and why it very much is a problem-solving test, and it's about working with the information you're given in a scientific context. So with the first one, we're being introduced to this Porson-Cand reaction. It tells us then we've got, it's a form of cycloaddition of an alkyne and an alkene combined with carbon monoxide to form a cyclopentanone. So looking at that, there's a lot of jargon, right? So if you're from non-science, this might be a little bit overwhelming to read. The key things that we want to really be paying close attention to is the generic structure, right? So we're being told that it's an alkyne and an alkene. So we know alkynes have something with a triple bond, alkenes will have a double bond in there. We're gluing those together along with carbon monoxide, CO, and then we're getting a cyclopentanone. Now, if you've done some organic chemistry, then you might be familiar with bits and pieces of this, and you might recognize, even if you've never heard of a cyclopentanone, you can sense pent being five-membered ring. It's got ene in there because it's still an alkene, because it does have a double bond in there, and it's a cyclic structure as well. So this helps us kind of familiarize ourselves a little bit. So this is just a generic schematic. I've kind of edited this and I'll make sure it's fixed on the resources page. I accidentally wrote R2 twice and everything was kind of off. So we've got R1 and R2 are part of the groups attached either side of the triple bond in alkyne. And then we've got R3 through to R6 being all of the attachments off of the double bond in the alkene that we're gluing together. And then carbon monoxide's getting involved as well. So then we're also told a bunch of information more on the stereochemistry of it. So the alkyl groups are attached to the double and the triple bonds are directed either into, which is going to be referred to as in, or out of, which will be called out of the plane of the page. And we generally use wedges and dashed lines if ever you've gone through any of the drawing of them. This is dependent primarily on the number of carbons in the alkyl chain, regardless of other attached substituents along the carbon chain. Where two or more alkyl branches have an equal number of carbons, the preference for in or out is determined by the molecular weight of any substituent attachment of the alkyl chain. So this is going through all of the scenarios. These are all of your rules being kind of created in the STEM. So we don't yet know how to know which one goes in, which one goes out, just that the length of the carbon chain is important. And when there are two or more, where they have equal carbon chain length, then we have to go to the molecular weight of other substituent attachments and that kind of thing. So we go down further, it'll keep explaining. Preferences for direction into or out of the page is measured by the alkyl branch's lambda value according to the table below. So positive values are preferences for in. So this is quite helpful now. So positive means it's going to go into the page, and I would make a note and write down that is a dashed line, like this, a dashed wedge. And then negative values are preferences for out of the page coming out towards us. So then that means negative numbers is going to prefer to have the wedge structure. We've got a bunch of numbers given for different alkyl branches and constituents here. So we've got methyl, ethyl, so just increasing carbon chain length. And you can see that lambda value goes up each time and goes more and more positive, meaning that that would be a preference for the into the page position. We've also got some other non-carbon, non-alkyl groups, so chlorine, bromine, hydroxide, and so on. There's no real pattern, there's just a bunch of different numbers there, right? And again, more negative means that it'll prefer to come out of the page, more positive into the page. And then in the cyclopentanone, where there are two alkyl chains attached, and this is a slight typo, I shouldn't have said alkyl, because these are not really alkyl chains, but ignore that. To the same carbon that have the same preference for in or out, the alkyl chain with the lambda value, slight typo, closest to 0 will be inverted to the position opposite to its preference. So what I've done there is basically just convoluted a much, much simpler concept that could have been worded more easily. So really what that's saying is when you've got two things that both want to go into the page or two things that both want to go out, the one that is closest to 0 has to flip and go the wrong way. A simpler way to look at that is the one that is more extreme, the one that is more positive of the two gets to keep its preference, or the one that is more negative of the two gets to keep its preference if they're both negative, right? So then moving along, we'll come up here for question 1. Consider the following cyclopentanone. Which of the following are possible identities of R3 to R6? So we're just looking specifically at this side of it. So the first thing we'd want to do is get some context. If we look at the general schematic, R3 to R6 are all coming off of the alkene, like this. So in terms of their positions, we don't know what it's been made from, and it's asking us just what are the substituents, not what is the whole molecule. So we can see that R3 points out, and R4 points in, and the same thing, R3 points out, and R6. Oh, that's because, hang on a second, R3, R4, that's R5. That's just my writing, I can't read. And then R6 is in, like that. So if we go through, it's just a case of process of elimination, we're just working through bit by bit. So if we look at R3 and R4, I would go straight to the options because there's so many different ways, so many different branches that there could be. So if we look at the first pairing in option A, this one has a propyl group and this one has an ethyl group. So we look to the table and we look at ethyl and propyl. We can see that propyl has the bigger positive number. And remember, positive means into the page. So the propyl will want to go in, and because it's a tie between the two, propyl is more positive, therefore it will get its preference to go in. So do we have propyl going into the page? Propyl was R3, and it's not, it's going out of the page. So already that has failed, just like that. What that also tells us is that, put it the other way around, you'll notice that all the answers use the same things, just in different arrangements. It means that R3 has to be the ethyl group and R4 has to be the propyl. So now I know it's down to B or C. This one's the same as option A at that point, so that one's out. So then if I go to the second one, it comes down to, they've all got combinations of H and F. So I might even just fast track this a bit now and go, all right, where's H, where's F? H is 0, F is negative 0.9. So the one that is furthest from 0 is the F, the fluorine, and that is negative. So it'll get its preference. And we've got our rules here, negative means out of the page. So out of the page was R5, like that. That should be the fluorine. So we look to the one that has fluorine in R5, and then we can see there it is there, out of the page, that one. And then H, then we'll have to default to go into the page, which is R6. And there we go. So therefore our answer is then going to be B, just like that. So it's a fair bit of work, but you can see it's not really relying all that much on chemistry knowledge, more so just on using the rules that that I've given in the question. The only thing you need to use here is to understand how to convert between names of compounds or branches and the chemical structure. That's the most common thing that you'll see being used. So question 2, which of the following is the product of the following reaction? So now we're just going forwards in the reaction and actually applying the pattern. So effectively, let's just quickly go back here for a moment. We can see that we're getting an addition of these two, and it tells us it's a cycloaddition. So in addition reactions, you usually have double or triple bonds gluing to other things and then losing one of those bonds. So if we actually try to trace where everything's coming from, we can see a double bond here. You would think maybe it comes from here, but then you'll notice that the attachments don't match up. It's attached to R1 and R2, which came from our alkyne. And the reason for that is when you're actually gluing these carbons together, you're actually going to lose a bond, and it looks like we're losing one of these, And then over here, we're going to lose one of this of the double bond and it'll become a single bond, which is what is happening here. So in this case then, it means that our alkyne comes from this side and then our alkene comes from this side. And then the carbon monoxide looks to be the C and the O coming from there. So we can now kind of account for everything in the structure. So now we're going to try to extrapolate this to what we've got here. So I would try to just draw it out and not look at all the options, because the options are going to be really similar and therefore it's very easy to get confused. So if I look at this, I now am going to draw out the pentene ring like this. I'll put the double bond in. This is where my triple bond was coming from, and that had a methyl group and then it had an ethyl group. So I'm just going to put methyl and ethyl like that. It could have been the other way around. We've got no information to tell us that they couldn't have been on the other carbons, but for now I'll just draw it that way. And then over here, again on either side, this is where the double bond would have gone. Now I can trace, and I might keep whatever's at the top. I've got chlorine and an ethyl group, and then here I'm going to keep skeletal, then I've got a methyl group and a propyl group. And then I look to the answers and I realize, hang on a second, I've got to play around with the wedges and the dashed lines. So I might try to rule some stuff out here. So I can see already D's not looking good. It's got a double bond in the wrong spot. So I'm going to rule that one out. All the others look identical on the left side. There's no difference. So it means I don't even have to bother looking for any extra features there. And instead what I'll do is look at what's happening on the side, and it looks to be playing around with all of the ins and outs. So in the first pairing, we've got chlorine versus an ethyl group. So I'm going to go over to the table, find those numbers again. So ethyl group is 2.8, chlorine is negative 2.7. And so out of these two, they're opposite. So ethyl will prefer to go into the page and chlorine will prefer to go out. So that should really help me knock some stuff out here. So chlorine's going to come out of the page and this will go into the page. So now I'm going to go straight to here and see what does that. This one's got chlorine going into the page, so that can't be it. This one's got chlorine coming out, ethyl going in, so that's good. This one's got chlorine out, ethyl in. So now I'll just look at what's the difference. The difference between these two here, and I actually didn't even catch it before. I got tricked by my own question. There's no double bond here, right? You'll notice that the bottom one here, these are identical. There's no difference there, so there's no point even testing it. The double bond is on this one. This one does not have a double bond. It should have the double bond in there as the remnant from the triple bond. So therefore, A will be my answer. So again, you can see that you don't really have to use any chemistry knowledge for that. It's all visual with reaction pathways. So then moving on, questions 3 and 4 for this stem. So which of the following reagents could be reacted with propine and carbon monoxide to form the following cyclopropanone product? Whole lot of jargon, but really all we care about are the bits and pieces. So we've got propine, carbon monoxide. So let's draw in propine. That would be 3 carbons with a triple bond on one end. And then we've also got the classic carbon monoxide to account for this bit. This is where our propine comes from. Means this is our alkene remnant over here. So if I just draw that out again, like this, I'm not going to bother with the wedges anymore because I don't care about three-dimensional structure. I've got chlorine coming off. This would have been a double bond. This is our methyl group. And then given that the other branches are not shown, this is skeletal. So it means that there's a hidden hydrogen on each of those. So I know that this is hydrogen and this is hydrogen. And I can basically just build back what it came from just by reversing the logic that was provided in the question. Again, not really using a lot of chemistry knowledge. In that one, really the only chemistry is coming from knowing that in skeletal structures, hydrogens make up the missing 4th bond there, right? Any ones that are missing. So now we just have to name this. So we go into IUPAC naming. And if you haven't watched my chemistry crash courses, go through those and I run through the process there. So we've got the longest carbon chain is 1, 2, 3 carbons long. So it's a prop. It's clearly a propene because it's got a double bond. And then the chlorine is going to go on the end, and that will be on the first carbon. So that will be a 1-chloropropene or possibly just a chloropropene. And we can see there, C. What am I doing? Option C is then going to be the answer in that case. So I'll change this question. There was a slight error in it actually, because I do these too quickly. At least one stereocenter rather than just one. If we go through and draw these out, if we draw the first one, 2,3-dimethylbutene, we'll draw in the butene like this, like that, butene, and then we'll put 2,3-dimethyl. So we'll put a methyl group here and a methyl group here. You'll notice that because these two branches are identical, you can't then make a chiral carbon out of this one when it attaches. Remember that the double bond will disappear and it'll become part of the pentenone. But the idea is that both of these will be methyls, and so will these here, like that. So you can't get any chirality, or you can't get a stereocenter out of that. So that won't work. So then if we try with B, 2-chlorobutene, we draw in our butene structure again, or butene structure. We put 2-chloro. The other one then is defaulting just to a hydrogen, like that. And now all of a sudden we have unique attachments on either end, like this, and on this. So then this here you would have CH3 and H, and then on this one you'd have CH3 and Cl, and you'd have a chiral center here and a chiral center here. So that one has at least one stereocenter. If we were to go through all of them though, the ethylene, just to rule them out, ethylene will be similar to the problem in A. So you'd have 2 carbons with a double bond, and you're only left with hydrogens to attach, which means that the branches are all going to be equivalent, so that can't be a stereocenter. And then finally, 2,2-dichlorobutene. It sounds like a good option, but it's basically putting both the chlorines on one end, which means again you get the same branching. And then you'll notice as well that if we do that, well, that's a bit messy. If we do that, we'll make our butene. This time now, we would have 2 chlorines on the second carbon, which is actually not possible because then you've got 5 bonds through that second carbon. So this is not even a possible reactant in any way, and that rules that one out. So then the answer to this will be B. Cool. All right. Cool. So then moving on, so now what we've got is a different unit, more like a biology maths graph unit. And we've got a 3D graph. I know people will kind of panic about these and stuff, so we'll go through this one and look at how to analyze these at the same time. So we've got sporacular fluttering is the ability of most birds species to alter their rate of oxygen consumption or oxygen uptake from inspiration, and that's going to be called a respiratory gain, measured in milliliters of oxygen consumed per gram of body mass per minute by altering the frequency of their wing flap frequency, flutter rate, right? Didn't have to say frequency twice. So there it's just defining all the key terms. So what I would do is let's write down over here, this is wing flap frequency, and then over here respiratory gain, and I would write down that respiratory gain is mils of oxygen per gram per minute, like that. And then we have, it's also found that tracheal length between the bird's mouth and its lungs can impact respiratory gain, and we can see that down here. And below is a contour graph representing the changes in respiratory gain in the hummingbird. So basically what we want to do here is a bird with shorter tracheal length will have. We've got shorter tracheal length, so we don't have a number, we just kind of push down the lower end. Look out for inverted axes. You'll notice that this is actually an inverted axis. It's got the large numbers on the left, small numbers on the right. And so if we're down this kind of lower region, then what we can do, I'll try to use a color that kind of contrasts a little bit better. We're down this kind of lower region, and that means that we're working in this kind of section here, anything, because we're not told yet about flutter rate at all. So a bird with a shorter tracheal length will have, and let's just go process of elimination, a lower respiratory gain at higher flutter rates. So if we look at that, let's actually see if that's true. At higher flutter rates, if we stay in this region, we slide up and increase the flutter rate, what happens to the respiratory gain? The lines increase. So we get an increase in the z-axis like that. So that would actually not make sense that lower respiratory gain gives lower respiratory gain at higher flutter rates. It would mean that higher flutter rates actually give us higher respiratory gain. So that one is out. Then we've got higher respiratory gain at all flutter rates compared to birds with longer tracheal lengths. So if we're looking at that, higher respiratory gain, it seems to get to a max of about this level here, which lines up to about 1.8, right? You can count the boxes. If this is 1.5, then 2, you can kind of wrap around the corner here and go, this is 1.5 and this is 2. So our line's a little bit below 1.8, a little bit below 2, so about 1.8. Higher respiratory gain at all flutter rates compared to birds with longer tracheal length. So if you look at that, if you increase the tracheal length, it clearly has a higher level to it. So that can't be it. Shorter tracheal length leads to lower respiratory gain. So that can't be it. Then we've got, does it have lower respiratory gain at all flutter rates compared to birds with longer tracheal length? Now this is a tricky one because it sounds like the complete opposite of B. You would think, oh, that's got to be right. But it's at all flutter rates, right? So if we look at the respiratory gain of something lower down, and I'll take the lowest one, 0.2. And then if I compare that to even something right next to it, 0.3, like that, technically has a higher rate, a higher tracheal length. You'll notice that if I try to extend parallel lines that are, it's going to keep straightening it, that are parallel to the axes on the back wall here, and then as well, I'll try to do one that is parallel to the y-axis, the flutter rate axis. Like this, you can see these two are roughly parallel, like that. I can then start to match up and compare the actual positions of them, and I can see that even at 0.3, it starts to get a higher flutter rate. So it doesn't actually mean, in this case, that the lower respiratory gain at all flutter rates compared to birds with longer tracheal length. The longer tracheal lengths, like 0.3, at a really low flutter rate, it can still have a lower respiratory gain than some of the shorter tracheal length birds with larger flutter rates. So the trick to it is because it says at all flutter rates. If it said at each and every flutter rate, then it would be true because the actual line itself for a shorter tracheal length is literally sitting lower down at every level. But because it's just saying regardless of flutter rate, we have to make sure that even the highest respiratory gain in the 0.2 tracheal length is lower than the lowest respiratory gain in the 0.3. And we can see that doesn't hold true, so that actually knocks that one out. And then finally, D is lower respiratory gain at lower flutter rates. So this one doesn't say at all flutter rates, and this is why this one will be correct. So if we remove some of this junk here, at a lower flutter rate, if we look at that, so we're down in this lower region, lower flutter rates down here, it'll generally have, we can read it either way, it'll generally have lower respiratory gain, like that. And so therefore the answer is D. With question 2, then we've got a bird with a flutter rate of 16 flaps per second and increasing, terrible grammar there, increasing their oxygen consumption rate from 1.5 mil of oxygen per gram per minute to 3 mils of oxygen per gram per minute. Its tracheal length is going to be approximately what? So if we look at this, what we have to do here, the important thing is that you'll notice that respiratory gain is actually measured as a fold increase, not the absolute amount. So a 2 actually just means that it's doubling. And we can see here that this is exactly what's happened. We've doubled it. So what that actually means is, it sounds like a change, and it's like, how could you pinpoint a point? But that's actually a 2-fold increase from 1.5 to 3. It's doubled. So we go to 2, and what I'm going to do is just draw lines in around something like this, and then I'm going to find the 2 over here, like that, and I'm going to create like a flat plane for myself, which will help me kind of work out where the height is for 2, right? I'm going to read the graph backwards. So then I'm going to find 16 for the flutter rate, which is this line here. And then thinking 3-dimensionally, roughly where will it get up to this flat plane or sheet of paper? It looks to be at around about this point here. And the way that I can confirm that is I can draw out more lines that are parallel to the axes and check that they actually hit at that height. And I can run parallel lines this way And again, it runs out to 2, so I know that I've mapped it correctly. And now I can read out from there over to this axis, and then I can see tracheal length of 0.4. I can determine the answer. And then finally, question 3. So if a hummingbird of mass 30 grams and tracheal length of 0.5 centimeters increases its flutter rate from 8 to 20, its respiratory gain will increase by what percentage? So let's get rid of all of this. So notice that it's a percentage change. So we don't care about the absolute value. So the 30 grams is irrelevant. You could go through and do the calculations on the energy and on the consumption and everything, but there's no need. So I'm going to ignore the 30 grams and just go straight to a tracheal length of 0.5. So that's this line here. I'll try to trace out what's relevant on the graph. Flutter rate's going from 8 to 20. So 8 runs me through from this position up to 20, which runs me to this position here. And I want to see what happened to the respiratory gain. So again, if I run those parallel lines like this, I can go out to either border and I can kind of get a sense of what the change has been. And that's actually not quite parallel. This. There we go. And it seems to line up with about 2 for the 8. And I can run out this way as well. Oh, it's not working. And it seems to hit at about 2. And then if I go to the 20, I might use yellow now. That's a little bit closer. I can see then that this one, oh, that's not parallel. So at 20, I can run a line that is parallel to this line. And it looks to be going up to about 3, or I could run parallel this way. And I can see it runs out to about 3. So I'm increasing from 2 to 3 as a fold change. So then all I have to do is just go, well, what's the factor of change between those two? It's 1.5, and that represents a 50% increase in the actual value. And so therefore the answer is A, like that. So it's more like a maths question than it is, it's not even a bio question at all. It's just a graphs and maths question. There we go. So that is one way that we can look at contour graphs. Hopefully drawing out the lines and things helps you kind of mapping them and reading them. It means that you can take a lot of the context out of the actual question as well and just look at it as points on a graph. There we go. Cool. All right, there we go. So I'll leave that one there. Hopefully that was helpful for people. Hopefully you got a few of those 7 questions correct as well. And hopefully the study's all going well, and I will see you guys in the next video.